Okay, we are recording. Am I audible? Can you hear me clearly? Like just for the quality of the video that we are recording.
Yes.
Okay. So we had been discussing about eigenvalues, eigenvectors, how we can factorize a matrix into. How can we factorize a matrix into? We saw last time if it was matrix was diagonalizable, we could factorize it into S inverse lambda S, depending on. So it depends on how you use the notation, but we saw that this was what we saw where what is lambda here, if you recall? What is lambda? Capital lambda is a
Upper triangular matrix.
no. I'm talking about the say the this is the eigenvalue decomposition,
Yes, the
diagonalization.
diagonal matrix.
I know it's a diagonal matrix. What does it consist of?
It consists of the eigenvalues of S. Sorry, A. Sorry, A.
Lambda 2, lambda n are the eigenvalues. And what is x? S here is
S
x1,
is an
x.
orthogonal matrix.
Not orthogonal. How every time orthogonal? Why will it be orthogonal? It's just a matrix with these being the eigenvalue, eigenvector corresponding to lambda I, right? Xi being the eigenvector corresponding to lambda I such that Axi is equal to lambda xi, right? You recall that we said that on this
Yes,
plane, this stays once you take a combination of these, well, according to this vector, the combination of the columns, it stays in the same direction. And we found out all the determinant and all the properties of it. Now I'll show you an interesting application. Uh, we'll do this in machine learning as well. We'll see this in PCA, but I'll show you another application that is very interesting. The first day, you may recall, I had done a gambler's ruin problem and we had used x to ut as x to the power t, right? We had used this as x to the power t as a solution, right? And then we had solved for x to the power t if we had a difference equation. You recall? We wrote if we had a difference equation in this form, xt equal to ax t minus 1 plus bx t minus 2, we took xt as some y to the power t. And you had questions, why did I take y to the power t? And then when we had multiple solutions to this, why did I take a linear combination of all those solutions? You had those questions. Do you remember? We'll see this in this. How does linear algebra and eigenvalues in particular help it? Okay, are you following or is there any questions? Okay, please follow. This is very interesting. So, you know from your school days, what is this called? What is this called? What is the sequence called?
Fibonacci.
This sequence is the Fibonacci sequence. So now, if I tell you to find the kth element of this Fibonacci sequence, what would you do? Like, so this is u0, u1, u2, dot dot dot, uk. If I ask you this question, what is the ukth element of the Fibonacci series? Fibonacci series, what would you say? You would write a program, a dynamic program, such that you'll take two pointers, you will store 2 numbers, add them and get the next number and keep doing it, right? isn't it? If you are told to find the kth value of the Fibonacci series, you would do it that way, yes or no? Or do you know any other way?
Yes.
So, but if I want a closed form, if I want a closed form for UK, what will I do? So let us write UT, the tth element. What will I do? Such that I'll just put it as a put the value of t and I'll get the tth element in O one time. Do you agree? O the tth element normal algorithm will be O n time? Yes or no?
I guess it's gonna be exponential, Moinakta.
Why will it be exponential?
The normal algorithm যদি find করতে না মানে by the recursion we do, it's gonna be
I don't know, like even in school, like in 8 and 9, they taught me only the dynamic program. They did not tell me to write it. Like this is a very simple algorithm. All you need is 2 pointers to store the previous 2 numbers. I want the best algorithm, right?
oh acha yes then it
Normal
is O of n.
algorithm for finding t is ON. This is school level stuff. This is not even university level. So what is it? You start a for loop for I going to 1 to n. You start a for loop for a I going to 1 to n, and you store a0 as 0 and a1 as 1, right? Or at minus 2 as 0, at minus 1 as 1, and you say at is equal to at minus 1 plus at minus 2. Now this becomes your new. So next what happens? At minus 1 becomes, or at minus 2 becomes at minus 1, and at minus 1 becomes at. And you keep on doing this. What is the time of this algorithm?
Yeah, this one is O of n. Yes.
So why are you saying exponential? See, the algorithm means always the best algorithm that is known,
Yes.
not some algorithm. I can always write an infinite loop and say exponential time algorithm in any algorithm, right? In any algorithm, I
Yes.
can write an exponent. So you can, like, that is meaningless. So this is O of n algorithm that is used to explain recursion, but in if you study programming properly, you will see that you will memorize or convert it into a dynamic program, which is much simpler in this case. Normally, in some cases, recursion can be easy, but here recursion is not even required. Okay. So, but if I'm telling you to find the formula for UT, what will you do? So
I can use generating functions.
See, I'll give you the hint. This I don't know what do you mean by which generating functions. You can use that, but again, that is exactly x to the power t you are saying, right? We discussed what is x to the power t, why is it, and why it is not, why it is the solution. So that's what I'll try to show. So what are the equations? Do you agree this is the equation that you have? Can I write this in this form? Okay. Now, how does it come to be a function of x to the power t? That's what we are trying to see. Can I write these two equations? Are these two equations correct? This is how you solve difference equation and differential equations as well.
But
I'll just show.
ut minus 1 is equal to ut minus 1 plus 0.
Ut minus 1 is equal to ut minus 1. That's what I wrote.
Yes.
This is 1 into I wanted to write this as ut minus 2. Right. Therefore, what can I write it? Can I write this way? Ut and ut minus 1 as 1 1 1 0, ut minus 1 ut minus 2. Can I write this from the first? This is where we began linear algebra, right? I'm expressing both of these equations in a single matrix form. Correct? Any doubts? Please feel free to stop me and ask. Otherwise, why am I going on doing this? I'll just start linear algebra, machine learning, and do linear regression.
Yes, understood.
So now I'm going to express this as, say, let me write this as xt. This matrix, this vector, this matrix as A, and this as xt minus, this will eventually become xt minus 1. Yes or no? Do you agree?
Yes.
So if I am able to find a general solution of xt, my first element of this will be my solution, right? Xt of 1 is the ut. Yes or no? Happy? I hope you are following. Okay, so if you are following, so now I'll just copy these two. Now it has become what? It has become a linear algebra problem instead of a sequence problem or a difference equation problem. It is now a plain linear algebra problem that we have discussed so many times. Okay. Today is 4/4/24. Now, what does this equation look familiar to? If xt minus was an eigenvalue, would it help you? Rather, if I ask you this question,
xt minus 1 টা তো eigenvector হলো।
yeah, just understand the feeling. If x0 I could write, or x1 I could write, if x1 was an eigenvector, what would have happened? What would have been x2 then?
x2 will be lambda x1.
Very good. Say associated with lambda. Now what would be x3, Uttrij? What would be x3? X3 is a into x2, right? From this generating equation or whatever recurrence relation. Yes or
Acha,
no?
then lambda x1, so lambda square x1.
Very good. Now see, if it was, so xt would have become lambda to the power t x1. Yes or no? Right?
Yes.
So now I would not have to do anything, just lambda to the power t and xt, I would easily find out the solution. Yes or no? But x1 is not an eigenvalue, right? Just see, what is x1? That is u0. X1 is, that is u1 is equal to 1 comma 0, right? This is what we want, right? This is x, this is x2 minus 1, that is x1, right? This is your x1. Do you agree?
Yes.
The u1th element is 1 and u0th element is 0, right? The x1 is u1 comma u0. So this is clearly not an eigenvector, right? So you just see, so 1 comma 0, if you multiply by 1 1 1 0, it changes to 1 1. So all our hopes and aspirations gone of converting it to eigenvalue. So now what can I do? Can you give me an idea? You should be able to give me this idea just now. Like one vector can always be written in terms of is the problem
basis vectors.
basis vectors are not and there's not any basis vector yet here. So are you clear that this is not going to work and therefore we need to convert, we need to have this to be some form of the eigenvectors, right? Is that enough an hint? If I can write it as a sum of eigenvectors, then I will be done. So any vector in 2D can be written as, what can I write x1 as? What is the dimension? What is the dimension of the space spanned by A? So what is the, how many dimension is X?
2 cross 1.
Two-dimensional vector.
Yes, so
So
R2.
what do I want to write x1 as? Are you not
I
following or is there any problem? I want
I
to write
want to write
hey,
x1 as means column space away, a combination of the columns away.
what is the objective? What is the objective? I want to make x1 an eigenvector, right? If
Yes,
it was an eigenvector, no matrix multiplication was required. So how can I make x1 to an eigenvector? If you don't ask, if you don't interact, what I'll just keep on relaying and you will just drop off the call.
no.
Let me write this as alpha 1. Let me express this as y1 plus alpha 2 y2, where y1 comma y2 are the eigenvectors of A. I can write this, right? If y1 is independent of,
হ্যাঁ ওটাই বলছিলাম y1 independent of y2, so they span entire R2.
so if I have two eigenvectors, I can always write any vector in terms of linear combination of the eigenvectors. Is it clear? Any questions? So this is the vector. This is the matrix. How many eigenvectors should it have ideally if it was diagonalizable?
It
If
must have two eigenvectors.
Yes,
Uh,
2 cross 2.
2.
two eigenvectors and hopefully they are independent. If they're independent, a 2 cross 2 eigenvector can map, can span how many dimension space?
R2.
So can we write it? Can we write Rx1 as a linear combination of them? X2 x1 is
Yes. X1 is the point.
x1 belongs
x1
to
is a,
R2.
yes, x1 is 1 comma 0, right? 1 comma 0, and you would have some y1 here and some y2 here, and you will take the linear combination of alpha 1 alpha 2 get this vector. I'm stopping again. Any questions? I'll wait for 1 second. Okay, no questions. Good. So now what should I do next? What should be my next step? If I know the eigenvalues and the eigenvectors, I'm done, correct? So what do I have to do? I have to find the eigenvalues and eigenvectors. So first step is finding what?
Finding the linear combination which x1 can be represented as.
That's what is our end goal. If we find that it is done.
We find A's eigenvectors.
So we need to need y1 comma y2. So for y1 comma y2, first step, what do we need for finding y1 and y2?
The eigenvalues.
So now someone else, how do I find the eigenvalues of A?
Like a minus lambda ti
Is equal to
minus
0. So this is determinant of t minus 1, t 1 and 0 or 1, right? Is this the 1? Yes, 1 1 1 0. So t minus 1 t. Correct? So what is this? T minus 1 into t minus 1 is equal to 0, which means t squared minus t minus 1 is equal to 0. So what are the values of t? 1 plus minus root 5 by 2. Yes or no? This equation is called the golden
Yes.
1 plus root 5 by 2 comma 1 minus root 5 by 2. This is called the golden ratio.
Oh, এটাই golden ratio.
Yes, because in nature always you have this number appearing. This is the solution of this quadratic. So now
হ্যাঁ
tell me
এই
what.
জন্য ফিবোনাকি সিরিজের যে এক্সপোনেনশিয়াল সলিউশনটা বলছিলাম না, ওটা I just one time told it is 2 to the power n, but one place actually told me I was wrong. It told me 5 to the power n, যেখানে 5 was the golden
We'll see.
ratio.
We'll see. We'll see. Exactly, that's what we'll find. It's proportional to 5 to the power n, not 2 to the power n. Why will it be 2 to the power n? Why is 2 is so special? Okay. So now tell me, what do I need to next find? My goal is to find the y1s and y2s. Yes or no? It may be difficult with these irrational numbers. So I will just find it in terms of t. Can you tell me in terms of t what are the, you should be able to tell me directly from with respect to this.
কি বললে বুঝতে পারলাম না। In terms of t মানে?
T is a variable, right? At the end of the day, it can take multiple values.
Yes.
I'm telling find the null space of this in terms of t.
আচ্ছা।
Because using these, you will see it is complicated. It can be like you may need to do a lot of normalization. It's not required here. You can just see the roots. If you have been following the linear combination of columns, you should be able to see the roots directly. So do you agree this should have a null space? So y1 comma y2 will be 0. Both will be 0. Yes or no? Y1 and y2 is in the null space of t minus. Yes or no?
yes, yes,
ay1 is equal to ty1. So a minus ti y1 is equal to 0. Similarly, t2 comma y2. Now I want to tell you, instead of using the values of t, which are there are two. So now see there are two values. So this is guaranteed to have independent eigenvalues. Yes or no? To have independent eigenvectors,
yes,
because it is diagonalizable. So we are happy about that. But let us find y1 and y2 in terms of t itself. So do you agree? I'll tell you. So this is simpler. So t comma 1 is a root to this, is a solution to this equation. Yes or no? Rather minus t comma 1. Because you should be able to see the left hand, the columns and tell me. That's why I was giving the hint. Minus t comma 1 is a, or you can even write t comma minus 1, whatever you like. Is it not? So what does the second column become if I multiply this? It becomes t into t minus 1 and denominator is t minus t. Yes or no? Okay. I hope this is too trivial for you. Is it
Yes.
0 comma 0? 0 comma 0, right? This is nothing but the characteristic equation.
Yes.
Oh, yes.
Good. So now I know the solution. So y1 and y2 I know. y1 is 1 plus root 5 by 2 comma minus 1 and y2 is, now do you see why do we get this that we have been discussing all this while? We get, why do we get end up getting a, what is it called, a linear combination of two solutions as we discussed last time? Now we can write x1 as we discussed, alpha 1 times 1 plus root 5 by 2 comma minus 1 plus alpha 2 times 1 minus root 5 by 2 minus 1, right? Which means, what does it mean? How can I get alpha 1 and alpha 2? That's what we need to find. Yes or no? Then only we will be able to find x1. Like x1 is already known to us.
Yes.
What is x1?
X1 is 1 0.
So how will I find the simple equation? Yes or no? The base cases are called base cases, as you always know. So
Yes.
so alpha 1 has to be equal to minus of alpha 2, correct?
Yes. Niche
From this second equation we'll get. Now I can easily write 1 is equal to alpha 1 plus root 5 by 2 minus alpha 1 minus root 5 by 2. Yes or no?
alpha 1 alpha 2 হবে না? ও আচ্ছা
Array
আচ্ছা alpha. হ্যাঁ
alpha into root 5. So alpha is equal to 1 by root 5. Correct? You agree? So
Yes.
now I directly know what are the values. I know that x1 is equal to 1 by root 5. এটা বল কি হবে 1 plus root by 2 minus 1 minus 1 by root 5. When you will do differential equations, you also go back and see this application in differential equations as well. If you are, when you're doing that, it's same way you can also solve differential equations. I'm not going into it because people are not interested that much. The differential equations in computers are also solved using linear algebra, using same eigenvalue, eigenvector solution. So everything in quantum mechanics is solved using eigenvectors and eigenvalues using matrices. So just a side note, people interested in physics can look it up. Okay, now I have this equation. Now if I have to find xt, what will be xt? Xt is अरे
Like
simple only. हाँ बोल. Let us write one. X2 let us write. X2 is बोल X2 क्या है?
A into this linear combination. Half হবে না ওটা? Half plus root 5/2.
I have written this together. You know, these type of things you should not even think about. Okay. Agreed? So next, what will this become? 1 by root 5 lambda times. So lambda 1 times. What is lambda 1? Lambda 1 is t, right? This only. This is lambda 1 associated with y1. This is lambda 2.
হ্যাঁ, ওই দুটো conjugate.
So I will get 1 plus root 5 by 2 into 1 plus root 5 by 2 minus 1 minus 1 minus root 5 by 2 into 1 minus root 5 by 2 minus 1. এবার O3 জামাই বল, what will this be? ATB or XTB? This is again the eigenvalue. Y1, Y2, lambda 2, lambda 1. What will it be? XTB?
like lambda 1 power n.
Very good. So lambda 1 power n or power t here into y1 or t minus 1, right? Here it is 2, so we got 1. Yes or no? Is there a mistake?
হ্যাঁ, এটা তো হোল টু দি পাওয়ার টি হবে, কারণ তুমি তো ল্যামডা 1 ইনটু ay1 হবে না একটা, ওখানেই তো আরেকটা
I don't
ল্যামডা
understand
আসবে।
what lambda ay1.
তুমি যে যখন x2 টাকে
This
লিখলে
is
1 বাই
x2,
রুট
yes or
5।
no? This is x2.
ইয়েস।
This is
ও
x2 is
আচ্ছা,
what?
হ্যাঁ, ওটাকে
This power
মাল্টিপ্লাই
is
করে
1.
হ্যাঁ 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 হ্যাঁ, ঠিক আছে তাহলে ঠিক আছে, ভুলে ফেলছিলাম।
So ut is xt 0th element, which is 1 by root 5. So now before I go into that, see, as limit t tends to infinity, what happens? I don't tell me it goes to infinity. One term, as t increases, what will happen? Right, use some common sense and tell me what will happen. 1 minus root 5 by 2 to the power t. Say t is equal to 100. What will happen to this term?
So this will increase, first part will increase lambda 1 because that is greater than 1, and
Yes.
lambda 2 is less than 1, so it will decrease.
Go to
So
0.
minus of that, so both will means together it will increase.
No, Baba, this in the limit, this will go to 0 or not? It will converge to 0.
Acha, to infinity it will converge to 0. Yes, yes.
Even to not to infinity. So even you have to find the kth term. This term is redundant. If you have to just do a, because this will grow very fast. This is going to grow, this is going to fall. So what will happen? This will fall. So the sum will, this will exponentially fall, this will exponentially rise. So the sum will still maybe increase and then be same, trace the other one. So that's why in books and all you will see this as the solution, lambda 1 to the power t minus 1 into lambda 1 as ut. Yes or no? So 1 by root 5 plus 1 by 2 to the power t. So this becomes a function of the golden ratio. Okay. Questions?
Like we have to take an integer of that because we are neglecting that
You
term.
can take like it will of course it be an integer, but it's an approximation to the Fibonacci series. Very close approximation.
Achha, achha.
Of course, you're right.
আচ্ছা
It's
মইনুদা,
yeah.
ওই ল্যামডা 1 হোল টু দি পাওয়ার টি মাইনাস 1 এর পরে ল্যামডা 1টা কোত্থেকে আনলে?
মাথা থেকে নিয়ে এলাম উড়িয়ে। এটা এখানে নেই এটা?
হুম, ওটা ল্যামডা 1,
I don't understand what you're
y1
saying. xt is equal to lambda t to the power minus 1 by root 5 lambda minus 1.
হ্যাঁ
What is this?
হ্যাঁ, তো ut ইকুয়াল টু হবে 1 বাই রুট 5 ল্যামডা। হ্যাঁ, ল্যামডা হোল টু দি পাওয়ার টি। ও হ্যাঁ, বুঝতে পেরে গেলাম।
Write in your paper and copy. These are not even these. If you ask this is equivalent to saying that I'm not doing anything. I'm just listening. If you're not noting things down, at least not noting things down, at least doing the calculation along with me, then these things would not cause any problem. So last questions or last part of this linear algebra module is what is known as singular value decomposition. We may touch upon some other things in linear algebra, but those will be in close proximity to machine learning. So singular value decomposition is a faster algorithm to, you can say, the advantage is it always exists. Always exist, unlike eigen decomposition, right?
Yes.
Unlike eigen decomposition does not exist. When is eigen decomposition does not exist, Otrich? When eigen decomposition does not exist?
Like
When
when arithmetic multiplicity is greater than geometric multiplicity.
Good. And then you will not have enough vectors to span the entire I space. Enough eigenvectors won't be there to span the entire Rn space, right? That's the problem.
Yes.
The second problem came when for non-square matrices, this eigen decomposition is not defined, right? Eigenvalues are not defined for, do you agree? Eigenvalues are not defined for square rectangular matrices. It's only defined for square matrices, right? Okay.
Yes.
So now I'll give you a geometric way to prove this. I'll show the form how it comes, and then if you are interested, I may show why it exists. But let's go to the geometric interpretation first. And don't ask why does this exist, because to show that it exists, we need to prove what I'll prove at the end. So let us see some few definitions first. So let us define the A to be a Rm cross n matrix. Okay, clear? Then I say the rank, and I say it's a rectangular matrix where m is greater than n. Just for example, right? If you can also be n is greater than m, and you can adjust accordingly, right? Once I show it for one, you won't falter as of now. So let us take this as an example. Then I'll complete the case finally when I'll be done teaching this thing. So this is one definition. Rank of A, I define as R, will be less than equal to minimum of m comma n. Do you agree?
Yes.
In this case, this is equal to less than equal to what? This is less than equal to m, correct?
Less than equal to m. हाँ ठीक.
Okay. So now what I do, I'll show you what exactly am I going to do. So let us draw this diagram first. So if I am going to write, say, AX, or let us write AU, what notation am I using? I'll just check once. Okay. AU1 as sigma 1 V1. I can write, this is not a problem. Any vector matrix multiplication. This is not a incorrect statement to write. U and V are different. What is the dimension of A? A is m cross n. What is the dimension of U? N cross 1. This is a scalar. And this is m cross 1. Yes or no?
Yes.
Some arbitrary equation. Okay. Now my question is, what does it mean geometrically? First, let us define all the spaces properly and their dimensions. Ball. Wow. We say this is the column space of A. It is orthogonal to which space?
Null space.
Bah. You asked the question in the first. Well,
A transpose, null space of A transpose.
you asked the question. We saw that column space of A and null space of A can have common elements. Row space of A and null space of A. Easiest way to remember is how? How many times will I do? What is the subspace of? What is column space a subspace of?
Rn.
I did not make out between M and N. What is column space a subspace of?
R R
R?
M হবে. RM. M small m.
Rows, because it is made by these column vectors, right? Spanned by
Yes.
column space is spanned by column
RM
vectors.
vectors.
Vectors which belong to Rm. Okay. Row space is a subspace of R to the power m.
N.
So is null space a subspace of R to the power n. This is a subspace of R to the power n. Now tell me, in this case, what is the dimension of null space of A transpose? What is the dimension of the column space?
Dimension of column space তো হচ্ছে না মানে কতগুলো linearly independent আছে ওতে?
So we have defined it already. Rank of A is equal to R.
ও আচ্ছা, rank of A equal to R equal to M. মানে it is
Equal
M.
to, no,
It
I
is
have
M.
not written equal to. I have written less than equal to.
Less than equal to.
Just R. Let me write R. I have written R, not defined R.
আচ্ছা R লিখলাম। এটা হবে n minus R.
N minus R.
না A transpose তো, হ্যাঁ সরি M minus R. M minus R. আর ওইটা হবে n minus R.
These should add up to N. direct sum, first class, first theorem. This should add up to M. Because they would span the entire Rm. Null space of A transpose and column space of A span entire Rm. Okay. Now, where does U1 belong to? And I'm going to write, say, sigma 1 is greater than 0 and sigma 1 is real. If it is not greater than 0, you multiply with V1 accordingly, right? I can always choose sigma 1 to be greater than 0, yes or no? Do you agree? And belong to real? Can you tell me why?
So or else multiply, that is minus V1
Good.
and
Well, mone kor sigma 2 negative. Mone kor sigma 2 is minus R e to the power I theta. This can happen. Sigma 2 can be any, sigma 1 can be anything. Correct?
you told real value.
No, sigma R tilde.
Achha, okay.
It can be any complex value, any number,
Yes,
right?
yes, yes,
Any
yes.
complex number. Because whenever we are coming to the realm of eigenvectors and eigenvalues, it can come up to be complex numbers because the roots of polynomials. Yes or no? Therefore, we have to.
Yes.
So now if I just multiply minus R minus e to the power I theta on both sides, I'll get R. And this I will say is sigma 1. And this I will go and multiply it with, I'll absorb it in V1. Right? So this I always write. Whatever is complex and whatever is negative, I can always absorb it in the vector, right? Always keep this in mind. So because we'll be using it later on. Is it okay? No queries? Okay. So now tell me, where does U1 belong to? Which space does U1 belong to?
row space key.
Say this is not equal to 0. Where does U1 belong to? It belongs to the, how did you say row space?
U1 is Rn. So
Just by matching dimensionality, you said.
yes.
True. But once you take the combination with respect to, when you multiply it with A, where will it become?
Column space এ যাবে.
This becomes in the column space. Okay, this is your V1. Sigma 1 times V1.
Huh.
Similarly, there is a, we'll show it if you are interested. There is a possibility that if we take U2 to be perpendicular to U1 such that even in this plane it remains perpendicular, then this is a correct way of doing it. So you will have R of these vectors, right? All being mutually perpendicular. Do you agree?
R of these vectors কেন ও আচ্ছা dimensionটা
There
তো
are,
R.
yes,
R, yes, R of these vectors they will span.
they will span the entire dimension, and I will get their corresponding. So the for now they exist. That is these orthogonal transformations. These orthogonal vectors even in the column space. This is your assumption. We'll show it if you are interested. I'm just keeping this assumption for the time being.
আচ্ছা
Yeah.
মৈনাকদা মানে so if say some ui dot uj equal to 0, so I have to basically show that aui dot auj equals to 0, তাই তো?
Not always will it happen. Only for special vectors will it happen. Special set of vectors. That's what makes it
আচ্ছা
singular
মানে
value decomposition.
ও মৈনাকদা, if ui is an eigenvector of তো এটা তো হয়ে যাচ্ছে।
That is a trivial case. If it is only for symmetric matrices, eigenvector if it is, then it will be true.
ও হ্যাঁ ঠিক, yes.
Okay, not always. Okay. Again, you're mistaking. You're doing the same mistake and again. Only for symmetric matrices does that happen. This is we have spoken about it many a times before.
না মৈনাকদা, আমি এভাবে বললাম যে if যদি ui ডট uj যদি 0
Okay.
হয়, তাহলে auI কে আমি যদি লিখি ল্যামডা ui
Yeah,
আর
yeah. Then it
auj
is
কে
true.
যদি লিখি
Then it is true.
ল্যামডা uj, তাহলে ল্যামডা স্কোয়ার ui ডট uj ওটা 0 আসছে।
Correct. Okay. So what I'll do is now I know a set of equation. Does this familiar? Does this look familiar to you? So I'll just write that set of equations. The A1 U1 is equal to sigma 1 V1, A2 U2 sigma 2 V2 dot 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 AN Vn, and I write this in such an order such that sigma 1 greater than sigma 2 greater than dot 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 equal to sigma r greater than 0. This order also is maintained by most softwares. Okay, does this set of equation look familiar? We have done a similar set of equations in the previous class. Yes or no?
Yes.
What are those equations we did?
ওই তো ওই eigen decomposition, I guess.
Yes. So again, what someone else, what will I do now? How will I stack them up and what will I do? Any idea? How do I stack vectors with each other, one after the other?
Like matrix form we can write.
Okay, you like this you're saying, not in R, right? This one, I'm keeping some space. There's a reason for it. This is what you're saying. This is how many dimensional? N cross R, yes or no? Am I writing? Yes, it is N cross.
Yes.
It is N cross R dimensional. So this will be, do you agree? Sigma 1 V1, sigma 2 V2. Matrix form, always try to write the block matrix. Sigma R VR, yes or no? This is again M cross R. Yes or no? I'm just stacking this column wise.
Yes.
So what do I get? I'll just keep some space here as well again. I will get A times U1, U2, UR. Some space I'll keep again. Again, I'll keep using V1, V2, dot 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 VR. Some space I'll keep. Then sigma I can write as sigma 1, sigma 2,
Column vector.
or sigma
Yes.
R.
No. Yes.
Diagonal matrix. Now is the time my design is not yet complete. My design is not yet done. I could have kept it to the R by R matrix, but then that would have been a tough thing to do. I need to convert this into, so how many, so this, do you agree U belongs to the R to the power N? ठीक ना भूल? U belongs to the
Yes.
R to the power N.
Yes.
So, and these vectors are in the row space.
Yes.
If I have to complete the matrix, from which space should I bring the rest of the vectors? Because I've already found perpendicular n perpendicular vectors in the row space. To find all the n vectors in the Rn, what should I do?
আরো n মাইনাস আরটা আনতে হবে।
From which space? Nikhilesh, from
ওর
which
থেকে
space? No, wait. Because wait, don't tell.
null space of AT. A transpose.
Very good. Null space of A, not A transpose. Row space is orthogonal to.
Yes, A.
So from here I can bring these design equations. Again, in perpendicular, it does not matter which of them I bring, right? In which order I bring. They have to just be perpendicular, because at the end of the day, multiplying would be 0. Yes or no? So UR plus 1, UR plus 2, dot 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 UN. These belong to the null space of A. I'm waiting for a minute. If you are following, let me know. Why am I doing it? You will see just now. Is this making some sense now? Do you agree now this is an orthonormal matrix? Yes or no? Orthogonal in null space. I'm still waiting.
আচ্ছা মৈনাকদা, মানে অর্থ নর্মালটা তো হচ্ছে যে আর এর যেগুলো U1 থেকে UR ওগুলো
This is a unitary
অর্থোগোনাল টু।
matrix. Just this is a unitary matrix.
হ্যাঁ মানে ওটা হচ্ছে, কিন্তু ওই UR+1 গুলো কি এই U1 থেকে UR এর সাথে অর্থোগোনাল হবে?
What? U1 plus R plus 1, the spaces itself are orthogonal. How many times will I do this? I've already done this, proved this in class, na? Row space and null space are orthogonal spaces. Every vector in the row space is orthogonal to the null space.
আচ্ছা দাঁড়াও, রো স্পেস নাল স্পেস অর্থোগোনাল, ও হ্যাঁ ঠিক আছে, বুঝতে পেরে গেছি।
But you know, why are you not revising this thing? 3 times I have done this. I'm drawing this. I'm putting the perpendicular sign here all the time. If that is not bringing a bell, that means you have not even seen the things once. Please give some effort. At least 10% of the effort I am giving you give, you'll learn everything. Okay, is that clear to everyone? So this is this is a unitary matrix. If I write this as UN Hermitian UN is equal to 1. Yes or no? Agreed? Because by all the vectors are, why is it orthogonal? Why it is unitary? All columns are
অল কলামস অর্থোগোনাল।
good. So now, similarly, V1 to VR belongs to the column space of A. Yes or no? So where should I bring the rest of the equation from? R cross M. So this is a R cross N minus R matrix. So where should I bring the rest of V's from? Bol re baba.
Null space of A transpose.
Yes. And it does not matter from where do I bring them. I will show you why. So VR plus 1. VR plus 1 dot 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 V M, right? This is R cross M minus R. ঠিক না ভুল? নাকি ভুল লিখেছি? This is V is M. This is N, sorry. M cross R, and this is N cross R. Is this okay now? I brought in M minus R from the null space of A transpose. Clear or not? Now to make
মৈনাক
left
দা
hand
ওটা
side.
m cross m minus r হবে না?
Yes, same only. I had it has not yet come to the screen, I think. I just rewrote it again. That time I had written R by just mistake. Okay, now do you agree that both U's and V's are now invertible? Yes or no? This is again an orthonormal matrix or a unitary matrix. V transpose V is V Hermitian V is equal to I, again by design. Both is
হ্যাঁ, b
clear.
inverse is equal to v Hermitian.
Part 3 is also clear. So Osmith, please go back and see when this weekend. Please go back and revise everything if you are interested. Yeah. So now, how do I convert this V1 to VR plus 1 to Vm? So left hand side, these columns will become 0, right? When I multiply A into U, these columns will go to 0. Yes or no?
হ্যাঁ, since they belong to null space.
But these are not 0 on the right hand side. So to make them 0, I should add 0 still. I go to n. Yes or no? Or in this case, how many m? Sorry.
একটু দাঁড়িয়ে যাবো মৈনাক দা।
I don't know. Left hand side is 0 from r plus 1 to n. Right hand side from r plus 1 to in the right hand side, r plus 1 to n is not 0. So how can I
Not
make
0,
them 0?
ওগুলোকে 0 বানিয়ে দেবো।
How do I make? From thin air?
0 বানিয়ে দেবো।
How to make it 0? These are not 0. These are not equal to 0. These are eigenvector. These
না
are
মানে
eigenvector.
ওই sigma 1 থেকে sigma r এর পর I'll start adding zeros না?
Yes, I will add 0 still. I can add how many zeros? Till n I can
ওই
add.
r plus 1 থেকে n, তাহলে n minus r খানা 0।
Okay, so now I have a matrix. This is, do you agree, our n cross n matrix? Yes or no?
n cross n matrix দাঁড়া।
N cross n matrix. Of course, it is n cross n because on the left hand side we have n equations and right hand side we have mv's. Yes or no?
n cross n matrix, yes.
There are diagonal elements which solves for my these are first r, and to solve for
হ্যাঁ
the next
ওইটা হয়েছে
n.
ক্লিয়ার।
Yeah. Now I am saying, but how do I make it conformable matrix? How do I multiply these matrices? So do you see, if up to n there is no problem, up to n, but in our case, what is n is bigger or m is bigger?
m is bigger.
Minimum is m.
না
m. N is bigger, right?
Like we can add more
N is
zeros, diagonal zeros.
Diagonal zeros we cannot add. Can you tell me why? So I can only go to m cross m here. M cross m. Yes or no? Because let me write this equation. Wait. This is just housekeeping, nothing else. So V is m cross m. Yes or no? U is n cross n. Yes or no? We just now wrote them.
Yes.
And A
m
is
cross n হতে হবে sigma কে।
yes. So sigma has to be m cross n, and we have seen sigma 1, sigma 2 dot 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 sigma r অবধি আমার কোনো সমস্যা নেই। সমস্যাটা আমার যখন আসবে when there is after, so even up to n there is no problem. Up to n I will just keep on adding, right? Not n, m, right? Up to m I can keep on adding 0. Yes, m is less than n.
But এখানেই তো diagonalটা শেষ, I can't add any more zeros.
Exactly, I cannot add any more zeros because diagonal ends here. But does that mean my life is doomed? No, I can add 0 matrix on the right.
Oh,
So this is this matrix is M cross M. When I add this will become M cross N minus M. And this total will become M cross N. Now it becomes conformable. Yes or no? I write this matrix as sigma. And I write as U Hermitian. This is called the singular value decomposition. Clear?
yes.
Similarly, if N was greater than M, what would you do? You would have added sigma 1, sigma 2,
Sigma
sigma
ওটা up to
N cross N করতাম,
n
করে
কোনো
নিচে 0
অসুবিধা
লিখতাম,
হতো না। হ্যাঁ
নিচে 0 করতাম। So this would have become again M cross N. Okay. আর equal to 0 হলে তো no সমস্যা only. Right? Clear? Okay. No doubts? Now, what I do next is, how do I find sigma? Sigma, I'll tell you how to find it, and then we can see if we are interested to see why this special orthogonal matrix actually exists. This orthogonal transformation between column space and row space exists always. That we can see at the end, because that is a bit technical, but very easy. If you are interested, it will just take 5 minutes. But let us first see what is generally asked. That is, how can you find sigmas? So sigmas can be easily found. I can tell you, I guarantee you that. Why? What is a Hermitian? Can you tell me?
a conjugate transpose.
No, this is A. All matrices can be written this way. Right? All matrices can be written this way. Can be written as SVD.
Yes.
So what is a Hermitian for this A?
A Hermitian U sigma Hermitian V Hermitian, কিন্তু যেহেতু sigma diagonal ওই জন্য
Not diagonal.
sigma
Sigma is
Hermitian,
real.
হ্যাঁ
Sigma
real,
is
yes
real.
real, ওই জন্য ওটা equal.
U V Hermitian. This is N cross M, M cross M, M cross N, N cross N, and A Hermitian is N cross M. Right? Now, what is a Hermitian A? A Hermitian A is
U sigma V Hermitian V sigma U Hermitian. ও আচ্ছা, এখানে V Hermitian বিটা মনে হয় I আসবে।
this is already we have seen. This is I.
I ও হ্যাঁ, এটা M cross N আসবে, এটা U Hermitian।
So this U sigma square, only the important part of N cross N remains here. Right? All this extra added cosmetic makeup is removed automatically when you multiply sigma and sigma Hermitian. Right? Let me write transpose for you to be easy. Sigma Hermitian is sigma transpose. Right? All the cosmetics, zero addition, rows and columns will be removed. Yes or no? you will only be left with sigma 1 squared, sigma 2 squared, dot dot dot, sigma n squared. Yes or no? I'm waiting. So,
Yes.
so this in turn, this matrix. For symmetric matrix, we had seen this is a symmetric this is not symmetric though, because A Hermitian A dimension, yeah, A Hermitian A is symmetric, right?
A Hermitian এটা Hermitian হবে, হ্যাঁ,
Symmetric,
symmetric.
which means all eigenvectors, eigenvalues are perpendicular, orthogonal. Yes or no? So A Hermitian A's the eigen decomposition we already know. না পাবো কি পাবো না? A Hermitian A
A
Hermitian
Hermitian is
tell.
eigen decomposition.
This is nothing but the A Hermitian is eigenvalue decomposition.
ও
A Hermitian
হ্যাঁ, ঠিক।
A Hermitian A I is, or say if you take x is sigma I squared xi. Yes or no?
হ্যাঁ, আচ্ছা, তার মানে মৈনাক দা, all these sigmas are square root of the eigenvalues.
You are not audible.
All these sigmas are square root of the eigenvalues.
Yes, so all sigmas of A are square root of sigma I, or if you will not get sigma square in this form, you will get some matrix lambda 1, lambda 2, dot dot dot, lambda n. So R plus minus lambda I. Like only plus lambda I will remain square root because it has to be positive, right? So it has to be lambda I. Again, when you get those lambda i's, you have to find the v's and u's. So finding u's and v is a bit difficult because you have to again solve a ui is equal to lambda v, right? These are not exactly the eigenvectors, not exact singular vectors. They are eigenvectors of A Hermitian A transpose, but they are not exact singular vectors of A, because negative or r e to the power I theta factors can be there, and you have to again solve for ai equal to sigma v to get it. But that's just once if you do it, you will understand. Take any 2 by 2 matrix and try to find a singular value decomposition, you will get. There's nothing much in it. So is this thing, the important takeaway is this, that sigmas are the sigmas of A, the singular values of A, values of A are what? Are square root of eigenvalues of A Hermitian A. ठीक ना भूल? Is it okay? Arey, again, where did you stop following me? Tell me. I'll explain that part. Like keeping on asking is a wastage of time.
I mean, last sentence you said, please repeat that.
Okay, can you tell me, did you understand this thing that all the singular values of A are the square root of the eigenvalues of A Hermitian A? That is clear?
Ah, yes.
Like from this equation, A Hermitian A we can clearly see is A Hermitian A is equal to U sigma squared U Hermitian. Yes or no?
Yes.
Yeah. And A, where A is equal to U sigma or V sigma U Hermitian. ठीक ना भूल? Correct?
Yes.
This part is followed. This is the beginning we prove. This is the singular value decomposition. And from
Yes,
there
Dada.
we okay. So but then A so now you see this sigmas are the same as this sigmas, yes or no? But it is easier on the left hand side because this is eigenvalue decomposition. Eigenvalue decomposition is easy to find. Eigenvalue decomposition. Eigen decomposition I'll do, and then I'll take the square root of lambda i's. If these give me lambda 1 dot lambda n, square root of lambda I will be the singular values. Clear? How to find the singular values?
Yes, understood.
Now similarly, if you understood, tell me what is AA
আচ্ছা
Hermitian?
মৈনাক দা,
All.
তুমি বললে যে u isn't exactly the singular
That's what I'm going to
vectors
show.
of a,
Yes,
আচ্ছা
that's what
ওই
I'm going to show.
নেগেটিভ হ্যান থাকতে পারে।
Yes, থাকতেই পারে, দেখতেই পাচ্ছি আমি তো। কারণ কি I am fixing lambda to be always positive, তাই না?
হ্যাঁ, if it has any negative part it will get absorbed, সেটা বললে।
Yes, yes, those things can, housekeeping has to be done. Let us see now, you will understand. What is AA Hermitian then? Just give me the closed form directly if you can.
u না, ও আচ্ছা, v sigma u Hermitian u Hermitian sig sig transpose।
Good. So you will have V sigma m cross m squared V Hermitian. ठीक?
yes,
Now again, up to R, there is no, again you will get from even from AA Hermitians eigenvalues, you will get the same eigenvalues. Yes or no? There's no difference. Up to R, you will not have any difference. Then you can have some differences from R to M. Right? Just to keep in mind. Because you can see, you may ask me, Dada, ki kore this is happening? Because on A Hermitian A, I am getting, what are you getting? A Hermitian A is V sigma squared n cross n squared U Hermitian. Right? So you will tell the dimensionality is not matching. How is it happening? But I will say only the first R will always be the same. Rest are all zeros, right?
yes,
So you can use either to find the singular values. But now you see U and V are not exactly totally related. Now when you're finding V Hermitian and V, you are not taking V Hermitian and V completely. What is the, so sigmas are always fixed, I know. But what is A? A is U or V sigma U Hermitian, yes or no?
yes,
Now you see here I have one V, one U, right? One V, one U, correct? But in these equations, I have two V's, right? Two V's. Here
ওটা
I
কি
have
স্কোয়ার হবে?
two U's. Where?
2u's
I have two U's. So when I am going to do the decomposition, do the eigenvalue decomposition, I will get some V, right? I'll get a fixed set of V's, which will be orthogonal. That is not a problem. Are you following? I'll get a set of V's. But there will be a problem because I have to equate them to AU is equal to sigma IV. Yes or no? Correct? I have to, this after
মানে এই
solving this,
জায়গাটা বুঝতে পারলাম না।
why are you thinking and not
Given
understanding? Just understand what I am saying. Just understand what everything I'm saying. 1, 2, 3. How will you get these values? V1 to Vn. You will get by eigenvalue decomposition. Yes or no? Eigen decomposition of of AA Hermitian, correct?
Yes.
You will get by U1, U2 dot 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 U N V M eigen decomposition of position of A Hermitian A, correct?
Yes.
You are not talking among themselves. So my idea is when you are trying to find the sigmas, the sigma square is always here, you will get positive number. Agreed? There is no difficulty in that.
Yes.
You have to guarantee it has to be a positive number. Now, once you get that positive number, you have already seen that they are real. So now you have to absorb the negative sign into V, right? Some way you have to absorb the negative sign into V. If there are negative values of sigma. So there comes the problem. In some cases, you can have negative signs like mismatched negatives between U and V. So you have to
सिग्मा नेगेटिव केन होते हैं ओ अच्छा प्लस माइनस
when
स्क्वायर
you're
रूट ऑफ
do
लैम्डा
yes, no, not plus minus, but when you're doing the eigenvalue decomposition of A Hermitian A, you have a matrix. You are not guaranteed to get positive eigenvalues always. Here, my definition was like that. You have to make the sigma squared positive. Even if it is negative, you have to put the negative signs into V. Like
হ্যাঁ আর না হলে
any
তো
A.
ইমাজিনারি আসবে
Exactly. So you cannot do that. So you have to put those negative signs accordingly into V's, right? As we discussed in the beginning. So there you can have a
ও
mismatch between the negatives and the positives. So you have to again calibrate it by solving for AU is equal to sigma IV. বুঝেছিস?
কেন মিসম্যাচ কেন হবে
একটাতে মনে কর A Hermitian A.
হ্যাঁ
Positive. Sigma 1. You have to check for the signs. It's real is guaranteed, but positive negative is not guaranteed. Na? When you are doing eigen decomposition of A Hermitian A or AA Hermitian, there can be negative also.
ইয়েস
That. AX is equal to lambda x, right?
হুম
It is also equivalent to saying if I just multiply minus lambda and write minus x over here, like put everything negative
ইয়েস
in these signs. So
হুম
if I had a negative sign over here and I had an x like this, so I have to
হুম
absorb this into the right hand, right? So say you have ax is equal to lambda x, where lambda is less than 0.
হুম
Or let us write to be exact, A Hermitian ax is equal to some lambda x, where lambda is less
ইয়েস
than 0.
হ্যাঁ একদম
But let us write lambda is greater than 0 because lambda is greater than 0 is equal to minus lambda. Okay.
হুম
So this, when I cannot take this minus lambda and do all the computations, can I do it? Because
না
I am forced to take positive. So now I have to
মাইনাস
do
এক্স বানাতে হবে
this. So the left hand side becomes positive V, negative left right hand side becomes minus V. Although
হ্যাঁ
they
এটা তো
stay
ইমব্যালেন্স
or
হলো একটা
exactly these imbalances may occur. এই এক্স্যাক্টলি এটাই বলছি যে ইউ আর ভি এর মধ্যে ইমব্যালেন্স থাকতে পারে, তখন তোকে সাইন গুলো ইউ হ্যাভ টু ম্যাচ এট দি এন্ড।
মানে আমি এ এ হার্মিশিয়ানের ক্ষেত্রে বলছি তো ভি হার্মিশিয়ানটা হয়ে যাবে মাইনাস
Not
ভিটা
all,
হয়ে যাবে প্লাস
not all. Some columns can be.
সাম
So
সাম কলমস
yes,
ইয়েস
that's why you have to again recalibrate using this sigma u's and v's, the negatives and the positives, because you are forcing yourself to be having positive values at the singular values. Okay. How does this singular value help you in square matrices? There can be many use cases, right? Singular values can be used because these singular values can be used to calculate determinants. Do you agree? If A is n cross n, singular values are easier to compute. There are more algorithms which are much more complex and easier than eigenvalue decomposition, which is beyond the scope of any even postgraduate courses. You have to take specialized numerical methods courses to know them. So we are not going into those. But singular value decomposition are fast to compute. SVD is very fast. When you're doing by hand, you may think that I'm still doing eigenvalue decomposition. Hey, this is too lengthy. But the algorithms that are there in the literature, that's very fast. You can look up some papers, they're very fast algorithms. So everybody does singular value decomposition. You may study PCA using eigenvalue decomposition, but the computer will always do singular value decomposition. So if A is n cross n, do you agree you will get some matrix M, sigma, and M Hermitian. Not M Hermitian, M1 Hermitian, M2 Hermitian, right? M1 into M2 Hermitian, because they need not be same.
Same,
Okay.
SVT.
But now I've still got a, I have got was sigma, which is diagonal. Similarly, in most new machine learning problems, you would often deal with A Hermitian A, which will help you to then become M1 sigma squared, M1 Hermitian. Am I writing it correctly? It's M2 Hermitian. So in that case, you would have similarity, right? This would be similar matrices. So these end up being, so A Hermitian A's and these sigmas, which are much useful in machine learning, because even covariance matrices are A Hermitian matrices, right? In those cases, if you just do the singular value decomposition, chatak say you will get the answer directly.
না মানে তুমি কি বলছো A Hermitian is similar to
A
sigma
Hermitian.
square?
Yes, it is similar to sigma square. So everything you do instead of doing the SVD, normally when you will be solving for your exams, you will be doing singular value decomposition, eigenvalue decomposition, but you don't even need that. Just do the singular value decomposition. You'll get the sigmas directly. Ekdam crazy as fast. Okay. Are you interested in knowing why it exists? Now we have assumed that this transformation from a perpendicular space to U's are perpendicular to V's are perpendicular, they exist. We have assumed. But are you interested in knowing why they exist?
মানে কি বললে? ও আচ্ছা, যখন আমি ইউ গুলো অর্থোগোনালটাকে আমি কলাম স্পেসে আনছি তখন ওখানেও অর্থোগোনাল।
Not always. There exists one such set. That's what I'm trying to say.
আইগেন হলে তো এক্সিস্ট হবে, ওটা একটা স্পেশাল কেস। কিন্তু
Eigen in square, I am considering rectangular matrices for the time being. Not even eigen.
ও এ তো ছিল এম ক্রস এন। ও
Yes.
ও মানে এসভিডি অলসো ওয়ার্কস ফর রেক্টাঙ্গুলার অ্যাজ ওয়েল, তাই না?
For any matrix it works. It is inclusive all matrices.
আচ্ছা, নাইস।
And it also gives you the same number of so if there are zeros, it means that is the rank of the matrix. Again, because they're similar, you can multiply and get the determinant of the matrix, and everything will work. If they're similar, you will get the rank of A is equal to rank of A Hermitian. Yes or no? So number of singular values is equal to the rank of the matrix. All these things you will get.
Number of singular
Rank
values
of
is the
A,
rank of the matrix.
rank of A Hermitian A is equal to rank of A. Yes or no? We have seen this. Rank of A Hermitian A is equal. Rank of A transpose A is equal to rank of A. If you have not seen rank of A transpose A, you haven't seen. So this is what dimension of. I told you one. Do you recall this equation? Rank of AB. I told you to revise
AB
is equal to rank of B minus dimension of null space of A into column space of B, or range space of A into column space of B. Just tell me which is the case. Range space of A into column space of B, correct. Oh, null space of A into column space of B, I think so. Yeah. So now tell me if it is AA transpose, then what will you get?
Rank of A minus dimension of null space of A ট্রান্সপোজ ইন্টারসেকশন ওগুলো তো অর্থগোনাল এন্ড ওগুলো আলাদা স্পেস, ওগুলোর মধ্যে কোনো কমন নেই তো সেকেন্ড হাফটা
Rank of A minus dimension of null space of A transpose intersection column space of A. So column space of A and null space of A transpose intersection is just the zero vector, not phi, zero vector. So this is equal to rank of A. Just let me check if I've written the equation correctly, because this equation you just should go back and please see this when you have time from the previous course. Yeah, I'm written it correctly. Yes. Okay. So that's why they have the same rank, and that is also equal to the rank number of singular values, right? Values, because they're similar matrices.
হ্যাঁ ঠিক
Greater than 0. So all these things from this you can get. Anyways, there's a side tracks, but why does it exist? I'll give you a overview, proof for it being for its existence. The proof is pretty simple. So do you see A Hermitian A is similar to A Hermitian? Can you prove this? Step 1 has to be this. How can I do this?
ফার্স্টে এ হারমিশনে আর এ হারমিশনটাকে লিখতে হবে একটু
A Hermitian is what? A Hermitian is what did I write?
ইউ সিগমা স্কোয়ার ইউ হারমিশন
U sigma square U Hermitian, and A Hermitian is V sigma square V
বি
Hermitian.
সিগমা স্কোয়ার বি হারমিশন
Now what can I do? So roughly speaking, we can do one trick over here. For the non-zero elements, I can do something like this. This is there. Although these are, be careful in when I'm writing this, these may not. So do you agree? A Hermitian A U Hermitian is equal to sigma squared, and this is
ওইটাকে ওখানে
what?
প্লেস করে দেবো
A
এন
Hermitian
ক্রস এন হ্যাঁ
n cross n, but this is m cross n, right?
এম ও ইট উইল অনলি হোল্ড ফর স্কোয়ার ম্যাট্রিসেস নাকি
No, just put zeros everywhere else. Put zeros
everywhere
accordingly.
depending
then
on who
I
is
can,
large
who is large, and then you can put A Hermitian is equal to V. What can I write?
b u Hermitian A Hermitian A UV Hermitian
Correct. Let me just give me one moment. Oh, but A Hermitian A, yes. So in this case, I can also write symmetric matrix. It's these are symmetry matrices. Is okay. Okay, so I can write this way. I can write. What can I write? You can just put this value over here, and I'll get U Hermitian sigma squared U Hermitian, then
U Hermitian
A Hermitian
A Hermitian A UV
V
Hermitian
Hermitian. And please, this is similar to this. Keep Dimensionality same by appropriately using zeros. Okay. Now tell me, if I use this, I can clearly see. What do I see? I have some matrix. This is a matrix. Let us write this as M, A Hermitian, A, B Hermitian. Yes or no? Do you agree? Correct?
हाँ M
Good.
हाँ.
Which also means this is equal to M, A, or you can write M, A Hermitian into M, A Hermitian, full Hermitian. Yes or no?
Yes.
Which is also, so this left hand side is also equal to what? A M Hermitian, M, A Hermitian. Do you agree? These are unitary matrices. M, product of unitary matrices is always unitary, right?
Product of unitary matrix is always oh हाँ ठीक ही तो हाँ UV Hermitian UV हाँ V Hermitian U Hermitian II হয়ে যাবে.
Yes. So you get AM Hermitian AM, right? Is equal to MA Hermitian, MA Hermitian, whole Hermitian, right? Agreed? The left hand side I just
Yes.
multiplied M Hermitian in between. Right hand side we got from the similarity transformation, right? So let us write
Yes.
A M Hermitian as some x. And therefore you have x Hermitian x is equal to x Hermitian, right? This is what we have. Yes or no? This is what you will get.
AM Hermitian কে x বলছো তাহলে
Yes.
x Hermitian x
No, sorry. So AM A Hermitian, right? So I have just written this wrong. AM A Hermitian. AM A Hermitian. Right? So this will be this. Right?
MA Hermitian MA Hermitian হ্যাঁ তাহলে x Hermitian x is equal to x Hermitian.
Correct. There is one special property of this. What is that? This is called this property. If A Hermitian is equal to A Hermitian A, right? This is called a normal matrix. Example is a what? If A is equal to A
Example
Hermitian.
is a Hermitian matrix.
Exactly, or a unitary matrix, Hermitian or symmetric matrix.
আচ্ছা মৈনাক দা একটা
Yes.
কথা মানে এটাকে দেখো A equals to A Hermitian is a special case which satisfies this. তো
Yes.
মানে
So I'm going. Don't if you are trying to tell some comments, just wait. Hold your horses. See, this is a symmetric matrix is a subset of unitary subset of normal matrices. The properties that you know is holding for only normal matrices. That is, if A Hermitian A is this is true, then A Hermitian A, then A is unitarily diagonalizable. There exists orthonormal eigenvectors. If this is true, there exists orthonormal eigenvectors. Now tell. Bol.
Oh, acha, mane symmetric matrices aren't the only one to have orthonormal eigenvectors.
No, all normal matrices have orthonormal eigenvectors. Why? We can just easily see that. This is your homework. Just prove this. What will you prove? Any matrix we discussed last time, and if you want to see the actual reason, can be written as a what? Yes or no? Schur's
Any
triangularization. Any matrix A can be written as this way.
Any matrix can be written as this way.
Yes,
Oh,
and I have shown it last time, and we discussed this last day also.
yes.
P is, let me just write this in a different format. So let us write this S. U only, U is I'm going to use. So let me use, what should I use? S. Schur's triangularization, let's use S. S delta is a triangular matrix where lambda 1, lambda 2, dot 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 lambda n. Any square matrix only. This has to be a square matrix. And you have elements on the top, below is 0. Right? We use this to show that the what is it called? We use this to show that the polynomial satisfies the characteristic polynomial, and a matrix satisfies its characteristic polynomial, right?
Cayley Hamilton.
Yes, we prove that using this. But if you want to know that proof of the Schur's triangularization, it is done in the previous course. Please go back and see. But your homework is just to show A Hermitian. You can use this result directly. So A Hermitian ki hobe? S
triangle triangle S Hermitian না এটাকে যদি লিখি আমি S
this is simple
Hermitian তাহলে
calculation. What is this? Just take a
Oh,
notebook and write.
ঠিক
Take a notebook in your hand and just calculate. If you're not following, this is the reason you're not following, because you're not calculating, because this is simple, just taking Hermitians and products of matrices. So I just put this value over here. So I'm going to put the value of A Hermitian over here. So what do I get? I get S Hermitian, S delta S Hermitian. Yes or no? So I get this. Yes or no? ঠিক আছে?
S A হ্যাঁ ঠিক আছে হ্যাঁ তো
not A, delta. Similarly, A Hermitian A is equal to S delta Hermitian.
delta Hermitian delta S Hermitian.
So you have to show that if these two are equal, then sigma Hermitian this is equal to this, right? This has to be true.
হ্যাঁ ও মানে সিগমাটাকেও নরমাল হতে হবে নাকি?
This is only true for triangular matrices. What is this? This is a upper triangular matrix, right? This is a lower triangular matrix.
Yes.
On the right hand side, it's a lower triangular matrix. and this is an upper triangular
and then
matrix.
upper triangle.
This only is true if it is true only if and only if sigma is or delta is diagonal. This is what is a homework. That is product of upper triangular matrix and a lower triangular matrix is equal to a lower triangular into upper triangular if and only if it is a diagonal matrix. This is your homework.
হ্যাঁ তো
Okay?
মানে কি হচ্ছে আপারের যেগুলো ডায়াগোনালের পর এক্সটেন্ডেড এলিমেন্টস ওটা ওই লোয়ার ট্রায়াঙ্গুলারের
I don't want you
জিরোটার
to
সাথে
tell the
মাল্টিপ্লাই
answers. Please do the solution, post it. This is a simple thing. You can just see it directly, but I want others also to see when they are awake. Now they are just not following totally. So that it's not useful to say. That you are saying is right because these elements will multiply with these elements too, and these elements will multiply with these elements. The product has to be 0, right? Or it has to be these two multiplications, right? That can only happen if these elements are 0, right? Yes or no? On the left hand side, this is multiplying with these. These
হ্যাঁ
are
হ্যাঁ
if these were non-zero elements, how can you multiply only zeros on the right hand side? It would not be possible. You can show that. This is the so the idea. The last thing is so now if it is so we know that if it is a normal matrix, it is going to be unitarily diagonalizable. Yes or no?
yes
For now SBD we have some results, right? We have M A Hermitian, right? Is normal, right? We showed it. We showed that
yes we showed it.
M A Hermitian, M A Hermitian is equal to M A Hermitian M A Hermitian, right? We showed this.
yes
But if it is normal, what will happen? Normal money, I will get, if it is normal, I will get one solution, right? I'll get, say, let us denote it by some here, give me some numbers, give me some m, so হয়ে গেছে n, some n matrix, right? Some diagonal matrix and n Hermitian matrix, right?
ঠিক এক্ষুনি we proved.
Correct. Similarly, just for I'm going to do it for ease of our understanding, since MA is also normal, some matrix MA is also normal. This is also normal. You can check that. This is just going to make our lives easier. This is what we don't even. Yeah, go ahead.
MA Hermitian যদি normal হয়, MA is also normal.
Let us see. Where is this equation? Do I get MA? Sometimes I always first only I get MA when I solve this equation, but I'm not getting this time. AM, because I took A Hermitian A. The other way around, it will be true, right? If I took M on the other side, it would have been MA would have been also normal, right? Understood? If I wrote A Hermitian A as M Hermitian A Hermitian M, instead of writing, I would make M on the left hand side. Then only it will work. Let us just take the MA case. You need not take MA case. It's not very difficult. This also is true. I was taking it because I wanted to show you in a different way. But anyways, so can I multiply this like this? M N Hermitian? Leave it. Don't think. When you will go back, you will think about it. Yes, I can write.
Hermitian M টা তো হ্যাঁ ঠিক আছে.
Just give me a moment.
Yes.
Hello. Can you hear me?
হ্যাঁ হ্যাঁ
Okay.
ওটা তো এমটা যেহেতু ইউনিটারি তুমি লিখলে।
Yes. So I can write A as M n Hermitian n Hermitian M. Yes or no? Am I writing things correctly? Just
এন
write
এক সেকেন্ড,
n Hermitian হয়ে যাবে n. This will come
এন
here.
এন হয়ে যাবে, আর ওটা সিগমা
This
ল্যামডা
will come
হার্মিশিয়ান এন হার্মিশিয়ান এম
n Hermitian M. ঠিকই লিখেছিলাম।
এম হ্যাঁ।
So now you see this. I have a matrix. Let me express this as some del D. Okay. Some diagonal matrix into n. This n has to be, this is a m cross n matrix. This has to be m cross n. Similarly, this diagonal matrix has to be, because we are accounting for all those n cross m, and this will become, n Hermitian m will become some other matrix. Say, let us write this as W Hermitian, right? Which is become m cross or n cross n.
হ্যাঁ ও ও এক সেকেন্ড, এটাই তো
So
না
now
এখনো আসেনি।
এখনো আসেনি because D can be complex, right? D can be a complex diagonal element. Yes or no? Because we have not done anything yet. But or any diagonal element can be written as the R into plus minus e to the power of I theta, right? So I will separate out the sigma matrix from the power matrix. Let me write the power matrix as E, the arc matrix as e to the power I theta 1, e to the power I theta 2,
আচ্ছা
dot.
ডিকে কেন বললে বিলংস টু কমপ্লেক্স? আচ্ছা দা জেনারেল
This is
কেস।
just general case. Exactly. This is a general case, so it can belong to any.
ও মৈনাকদা, তুমি যেহেতু সিগমায় আর রাখছো, therefore sigma is the real part. হয়ে
Yes,
গেল,
the
the
real
real part
positive
gets
part,
out.
real positive part.
হ্যাঁ যেহেতু
And
যেহেতু
yes,
ম্যাগনিটিউডটা প্লাস।
and so I will now, you can replace this as U sigma V Hermitian as A. So this exists due to this normal case. But the geometry is good to keep in mind. This will not come in your exam. That is for sure. But the geometry, if you keep in mind, and if you are inquisitive and you want to know why is the case that it must exist, then this will give you the answer. Okay.
Yes.
Others, if you have not followed the last part, please go back. Please see the video once again. If you have any questions, queries regarding anything, you can ask me now related to this chapter that we have been discussing. So we couldn't start in machine learning today. We'll do it next day. We have completed linear algebra totally, and you can happily do the homeworks now. And I'll drop a mail if people want to join more people. It will be good. It is good that we are starting machine learning on a different day. than doing it together. So next day is I'll just give you a brief overview what we'll do next time. So we'll see what is machine learning, and we'll see what is its application in today's world. And then I'll be going into what is linear regression in one variable, touching about a bit of optimization. And I'll show you how to code linear regression. I'll give you a general case. I'll show you how linear algebra can be used to model linear regression. And then finally, we would learn what is gradient descent. This is the plan for the next day. Tell your friends if they are interested to join. They are welcome. Also. Good. So any questions? Any questions regarding things we did today? I taught what is SVD and the uses of eigendecomposition and decomposing matrix into this diagonal matrices, some rotation matrices on the either side of the diagonal matrix. How it can be extremely useful. We'll see in machine learning when we do PCA and so on. Okay, any related questions? Okay, I'll stop recording.
আচ্ছা এই ভিটাকেই মনে হয় this v is only called the right singular vectors and u is called the left singular vectors.
Singular vectors, and these can be used to find inverses also. The Roger Penrose inverse uses this.
Achha.
You can easily find inverse, right? So you can take identity matrix on one side and use these matrices like V Hermitian, sigma inverse U will be your A inverse, your pseudo inverse. That is called a pseudo inverse.
ওটাই তো pseudo x transpose x whole inverse x transpose.
Yes. So you will get your pseudo inverse only from here. We'll see what is a pseudo inverse in linear algebra as well. But even from this SVD, you will get the single value, your pseudo inverse. From your left and right.
Fine.
Okay, so I'll stop recording, and other questions regarding assignments I'll take after I stop recording.